Alright, this is our waves video 3. We're going to talk about the anatomy of a wave. So we've done a lot with period, pendulum, springs, but what is a wave really? Today we're going to find out and see if we really like waves. Alright, first we have to learn the parts of a wave. The crest is the top, the bottom is the trough, amplitude is the distance from the middle all the way up to the top. All these little guys, D, G, I, and this guy not labeled here, these are called nodes. And anywhere where you are the furthest maximum amplitude away, that is an anti-node. So you have crest, trough, amplitude, and you also know that a wavelength is the full up and down and back to my position of equilibrium. So this is one wavelength as well. So now we have all the parts of the wave. What are we going to do with these? First, we have to know all the types of waves. So there's two types of waves. A transverse wave is waves where the direction of motion is perpendicular to the energy. So these are all the waves that we typically draw. Ocean waves are transverse waves. Most of the waves that we think of in terms of wave dynamics are transverse waves. The other type of wave is a longitudinal wave. And this is where the wave direction of motion is parallel to the energy of the wave. So this is like a sound wave would be considered a longitudinal wave. There are other longitudinal waves, but sound is the best example of a longitudinal wave. So we need to know the difference in how each of these waves moves through a particular medium in order to transfer energy from one area to another. Equations with waves. Alright, so waves are fairly simple. If we think back to what we learned in terms of the first equation, velocity equals the change in distance divided by the change in time. Well, wavelength upside down y, lambda over here is a distance. So if I start in this position and the wave goes one full wavelength, I have a distance equal to that movement. So lambda over here is a distance. And we also know that the period is the time to do one full oscillation. So it's the time it takes to go one full wavelength. So we have two perfect qualifying variables that say lambda is a specific distance for one wavelength, and the period is the specific time to do one full wavelength. And we also know that t is equal to 1 over f, so therefore we can also write velocity is equal to wavelength times frequency. So that's how we derived this equation from velocity equals distance divided by time. Let's see how useful that can be. Alright, here we have two waves. This is the idea of superposition and overlapping. So we have constructive and destructive interference. As this wave is moving over here to the right, it's going to overlap with this wave to the left. As this guy continues to move over here, he is going to occupy this space. So here I have a positive volume, and here I have a negative volume. These two are going to cancel each other out. So in the end, as these two waves move over past each other, the only thing that I have left is this negative volume as defined down here. So this negative volume matches this negative volume down here. So we have to think of how these two waves are going to interact as they interfere constructively and destructively with each other. Here, because I'm taking away, this is destructive interference. In other cases, where I have two waves that both have positive amplitude, as they interfere constructively with each other, you would basically add the blocks on top of each other just like this. So it's just basically thinking of how waves interact constructively, positive, and destructively, negative with each other. All right, here's the last part. Now we're going to do wave analysis. So here they're showing a wave. Based on the information provided in the graph, what is Vmax for the oscillating mass at the end of the spring? Sounds really hard, but it's fairly simple if we know how to approach it. First off, we have to look at what values are given. Through the problem-solving process, which we all love to do, we can tell that the amplitude is 0.5 meters. It doesn't give me the wavelength, but it does give me the period. T is equal to 0.1 seconds. All right, so I'm going to need two equations in order to solve this, because I don't have one equation that fits all these variables. So I'm going to say T is equal to 2 pi, and then inside the radical, I have K over M. And I also know that V max is equal to A times M over K. Pretty sure those are flipped. So here this is K over M. Goodness. M over K. There we go. And K over M. Right. So if I know the period is 0.1, so over here I'm going to get 2 pi and put it over here underneath the period. So I have 0.1 divided by 2 pi is equal to square root of M over K. If I distribute the square, what happens if I take the reciprocal of that and flip it? So then I say 2 pi over 0.1 is equal to square root of K divided by the square root of M. Well, that is the same thing as this. So then I can just insert 2 pi divided by 0.1 times A, which is 0.5. So 2 divided by 0.1 gives me 20 pi. Half of 20 pi is 10 pi. So something that looks really hard in the end, not too difficult. All right, there you go.